Hello, welcome to Maths with EJD. In the previous video, I talked about minimum spanning tree with Kruskal's algorithm. First of all, introducing us to the idea of minimum spanning tree, which is simply a subset of a network that gives you the shortest pathway, within the network, so to speak. And we see that that is useful for different situations like in connecting cities with cables, or connecting cities with road networks, or any other connection you can say, or maybe even maybe gas supply within cities and things like that, so you can get easy pathways like that. So here I'm using, so there we talked about the Prim's algorithm also, which involves, start choosing a random vertex and then going from each vertex in the minimum spanning tree and choosing edges that are small edges, as small as possible, that won't lead to closed loops. And then we saw how we have arrived at that the other time. So let's check out what Krukal's algorithm is about. So minimum spanning tree with Krukal's algorithm. So I'll just go straight to that. The Kruskal's algorithm is another method for finding the minimum spanning tree. Minimum spanning tree. After now, I'll just call it MST. So it works. So here, for Prim's algorithm, you start with a random vertex and then select small edge, the smallest edges until all the vertices come into the minimum spanning tree. So here, for Kruskal now, it actually works by sorting all the edges. So you sort all the edges. An edge would be like from A to B, B to C, C to D, and things like that. So it works by sorting all the edges in the graph by their weights. Sort by their weights, and then adding them one by one to the minimum spanning tree, as long as long as they don't form a cycle. As long as they don't form a cycle. This is a greedy algorithm. So we have this idea of greedy algorithm, which ensures that you want to incur the smallest cost as much as possible. So that's the idea of greedy algorithm. So let's go ahead and talk about steps. Of course, that's actually implied from what we've said already, but let's just emphasize it. Steps to apply Kruskal's algorithm. Okay, the first step is to sort all the edges. So for prims, right, you choose a random vertex. Here you edges, sort all the edges in increasing order. Sort all the edges in increasing order of their weight. First step. Then the second step will be to add edges one by one, add edges. So, I mean, this one now looks like the Prim's algorithm a little bit. Add edges one by one to the minimum spanning tree, ensuring no cycles are formed. So you don't want to have a closed loop like ABCA like that, or ABCDA. So add edges one by one to ensure, I mean, to the minimum spanning tree, ensuring no cycles are formed. You don't want to have a closed loop, just like in the Prim's algorithm. Then the next thing is just repeat, repeat step two until all vertices are connected. Until all vertices are connected. Okay. So well, let's take the same example like before. Um, example. Or I can even change the, okay, well, let's just use that. An internet service provider seeks to network five cities, A to E, um, with internet cables. So find the minimum spanning tree and the attached costs if the cable costs are given in the table below are given in the table below. Okay, here's the table now. We have city pair and we have the cable cost. So from A to B, the cost is $4. Then from A to C, the cost is $2, just the same problem like before. Then from B to C, the cost is $5. From B to D, the cost is $10. From C to D, the cost is $3. Then from C to E, the cost is $8. And lastly, from D to E, the cost is $7. Okay, so that's what we have. So from this algorithm, right? Of course, we want to find the minimum spanning tree and the attached cost. So here we just say, okay, let me just go and say solution, right? The solution. So we already know what the steps are. The first step is one, sort the edges. Sort the edges by weight. Okay. Sort the edges by weight. That's the first thing we have to do. So you go back up there and see this should actually be the smallest. That's A to C, $2. Then next is C to D, $3. Next is A to B, which is $4. That's number three. Then we have B to C, $5. That's number four. We have D to E, $7. That's number five. We have C to E, which is $8. This is number six. Then B to D is $10. That's number seven. So we sort all that. That means we have AC, CD. Okay, we can attach the cost to AC is 2, CD is 3, AB is 4, then BC is 5. We have how many in all? We have 7 in all. So we have AC 2, CD 3, AB 4, BC 5, DE, DE is 7. Okay, that's 1, 2, 3, 1, 2, 3, 4, 5. Or let me take DE down. DE DE is $7. We have CE, which is $8. And lastly, BD, which is $10. So we have those. So that's the first step. Sort the edges by weight. So the next thing is to add the smallest edge. Add the smallest edge. Add the smallest edge. And of course, you can see the smallest edge is AC is 2. Add the smallest edge. That's AC 2. Okay. AC to the MST. So in that case now, here we have the current cities in MST will be cities in MST. Here will be A, comma C, based on what we already have for now. Okay. So the next thing is step three. So step three, okay, I mean, this is, so we just take it. Then no, step three now, the next thing you're going to do is again, add, add the next, add the next smallest edge, and that is CD with $3. Okay, that's the next smallest edge to the MST, right? To the MST. So in that case, that means that okay, I was supposed to change that, right? Okay, I mean, let's just leave that the way it is. So that means now the cities in MST, the cities in the minimum span network, the minimum spanning tree will now be the AC you had before, and then uh D has joined now. You have C coming in again, so you don't repeat that. You just have ACD. Okay, so that's that step. Then um okay, let me just change. So step four now, you add the next one again. Add the next smallest edge. Add the next smallest edge. The next smallest edge, as we know, because we've done this, the next smallest edge is AB4. Okay, that is AB4. Okay, so now that introduces B into the loop. So we now have cities in the minimum spanning tree. We now is now A, B has come in now. So you have A, B, C, D. Okay. Now, again, you add the next smallest one, which is B. Okay. Now, if you add, normally you should add BC, right? But if you add BC here, we already have BC. So it means it is going to lead to a kind of closed loop again. We are going to have like a closed loop since we already have B and C here. So having if you are going to add anything, it should just be you have at least you should have one new vertex in attachment. So if you put BC here, you're going to have like a closed loop. So uh BC will not be able to join that, right? So then we have to automatically go to the next one, which is DE. So you can see any new thing you add, right? So D is here, but E is not there, so it's fine. But if you add BC, that's a good sign that you're going to have a cycle, a closed loop, which we don't want. So let's go for um step five now. So in step five, we skip um skip the next smallest edge, the next smallest edge, which is actually BC5. It is actually BC5 because because the the two vertices B and C are already in the minimum spanning tree. This is to this is to avoid this is to avoid a cycle. Okay, this is to avoid a cycle in the minimum spanning tree. Okay, so that's what we do for that. Now you go to the next step, that is step six. So for step six now, since you have skipped BC is 5, You add the next smallest edge. The next smallest edge after BC is DE. So DE is fine because we don't have D and E. We have D in the span already, in the minimum spanning tree, but we don't have E, which is okay. So add the next smallest, add the next smallest edge. Okay. And that is DE. DE is actually 7. Okay. Okay, I guess I should have, let me update for step 5. Let's update the minimum spanning tree since we have skipped something. Okay. So what this simply means is that the cities in MST will remain the same. Cities in minimum spanning tree will still be the A, B, C, D. A, B, A, B, C, D. Then we now go for step 6. Add the next smallest edge, add the next smallest edge. So with this, even without drawing the diagram, you are good to go with the Kruskal's algorithm. Add the next smallest edge, which is DE $7. Okay, DE $7. So now if you do that, it means that you now have the cities in the minimum spanning tree now will now be A, B, C. So from D now you can reach E. Okay. So from D now you can reach E. And since there are 5 cities in all, we have cities A to E. So at this point, you don't have to worry about C, E, and BD because you have reached all the vertices. So maybe I can just make that into like step 7. So stop stop the process, stop the process. Since all five, since all 5 cities or vertices have been reached. Okay. So after stopping the process, then we have to now make the total cost, right? So 8 now, here we stop the process. So 8, we now compute the total cost, compute the total cost. Okay. So once compute the total cost, so we know that the edges selected are AC, AC2, CD3, AB4, and DE7. So the total costs can be computed as follows. Okay, so you have total costs equals 2 plus 3 plus 4 plus 7. 2 plus 3 is 5 plus 4, 9 plus 7, that's $16. Okay, so that ends it. So using the Kruskal's minimum spanning tree, using Kruskal's algorithm, the minimum spanning tree connecting all cities is achieved with a total cable cost of $16. So let me make that note. Using the Kruskal's algorithm. So it's just the same value with the Prim's algorithm. So using the Kruskal's algorithm, the minimal spanning tree or the minimum spanning tree, the minimum spanning tree connecting all cities, is achieved with a total cable cost of $16. So with that, we come to the end of this. If you have not subscribed to the channel, be sure to do that right away. Hit the notification bell so you can always get alerted each time a new video is released. And don't forget to comment. Let me know if you want me to teach a topic or solve a problem. And like and share so that more people can have access to this great learning. Till I come your way again, have a nice time. Bye.